All right. Who here knows what assembly language is? All right. Have any of you ever had to do it? Yeah, it doesn't feel quite as easy as those higher level languages, right? But that was the only way to do it at one point. And this woman invented them. And she just died, so I thought it'd be nice to highlight her, and you can learn about her. Kathleen Booth, inventor of assembly language. Thank you, Kathleen Booth. All right. Before I get into more stuff about neural networks, what questions do you guys have for the homework? Any? We had a good number of people come to office hours today. That was good. Good to see you guys. No questions? All right. Enjoy your homework. Okay. This is where we left off. And we're about to make it more complicated. So, as a reminder, you have our current neural network that's taking in things step by step, but we decided we're going to have character-based LSTMs that do that with these characters, give us a vector. We also have a vector that we got off the shelf, glove vector. And we realized that we just put them together. That makes a longer vector. And then we have the LSTM going one way. And anybody remember how, if we're at this stage, we might want to get information from the word over here. Do anyone remember how we got that? Yes. We're also going backwards at the same time. And then we get two vectors, one from this, one from this. We concatenate them. Those go into the final predictor, which is a CRF layer, conditional random field. That's a special kind of Markov field, which we're going to get into. Now, did we show this slide last time? Good. Okay, so graph theory is just the mathematics around when you have a bunch of dots connected by lines, but it has real world applications. And it started in Königsberg. Euler was trying to think about, is it possible to cross all those bridges once? Turns out it's not. You end up crossing at least one bridge twice. And he proved it with graph theory. Graph theory is a beautiful way to analyze things that connect, have to agree with each other or not sometimes. Here's a very simple graph. We only have 4 nodes. And these 4 nodes have tendencies. And we describe those tendencies with this stuff here, that stuff, that stuff, that stuff. Some people call it a partition function. Some people call it all kinds of things. So let's look at the one at the very top. That's D and A. What it's saying there is that, remember, this is very simple. We're actually going to give A, B, C, and D the ability to be a 0 or a 1. That's it. Which makes the rest of the math very simple. So at the top, if D is a 0 and A is a 0, they both like that state. 100 represents how much they like that state. If they disagree, you know, if one's 0, one's 1, then it's a 1. That means they don't like that. And of course, if they're both 1, they like that. So A and D really like to agree. A and B, oh, they got some mixed feelings, right? So maybe they prefer to agree at 0. They don't really want to agree as much as 1. And they're in the mix on the other 2 a little bit. They really don't like this state where A is a 1, this is a 0. Now this one's simple again. They just want to agree. And here, these guys just want to disagree. So the question is, how do you determine the quote unquote best set of values? Is it, A is 1, B is 1, C is 0, D is 1? What is it? What's the best? And it turns out you can use all these values, you can just add them up, and you get this whole big long thing, unnormalized. Some of them add up these states, A0, B0, C0, D0, that adds up to 300,000. But it turns out this is the one that's most well liked by everybody. It's like a voting system. And that gives us this final state. And when we normalize everything, we get probabilities. So A0, B1 for the A and the B. And then you have, if you look back at this one, A0, B1, C1, D0. That is the state that the system as a whole likes to be in the best. Now try to take a mental leap and guess, how would we apply this to identifying entity types, person, location, time, organization? Yes, exactly. Think about this. If you have a statement like blank went to the blank. Let's say I told you that one of these is a person, the other one's a location. Which is which? You guys don't know, right? This has got to be the person, and this is the location. And you know it because of the relationships things near each other tend to have in sentences. And that's what your CRF will try to learn. And instead of being in a circle, it's going to be more, it'll be drawn out. It'll be a row. But that will give us the ability to decide, is it a person, location, or whatever. Now, Markov random fields and CRFs are related. The only difference is that a CRF is a Markov random field where these depend on some inputs. So for Markov random field, these are always the same for some set of points. But if you want to be able to change them based on the inputs, then they call it a conditional random field. These things came out of physics. So that top layer, it uses not only this vector, but it uses knowledge of what's next to it. And if you think about all the possible things everything could be, it could be not an entity, it could be a person, it could be internal to a person, or the beginning of a person tag. So it can run through all of those possibilities and decide on the one that everybody likes best. In the same way we decided on the zeros and ones for the ABCD. It's a good idea, isn't it? Any questions on that? All right. This is, let's get back to this. Okay. We talked a little bit about object recognition and the need to have these different angles. We talked about this, right? Yep. Now, you get funny cases like this. If you take a typical facial recognition system, you will have some lower level filters that will be looking for a mouth or a nose or an eye or another eye. And this image will trigger it to say, yes, that is a human face. And it won't know that there's anything wrong with it. And it's because information is lost in the typical neural network. The typical convolutional neural network will have something called max pooling, which means that from all the possible values, like let's say you have a filter that's looking for noses, right? And it scans across an image and it finds a nose. There's no information about that nose's relationship to other elements. So this is an example of an adversarial image. An image which it wouldn't see in nature typically, but if you show this image to the neural network, it will say, yes, that is the face. There's nothing wrong with it at all. Normal face. You won't know the difference. That's why Jeffrey Hinton, the guy who really kept neural networks alive and a research topic for so long, he has also won the Turing Award. He came up with something more recently called capsule networks. So CNN stands for convolutional neural network. Convolutional neural network will be like this. It will just take these things separately, whereas the capsule neural network will be able to understand the relationship between the different objects. Are they in the right pose and position with relationship to other things and size as well? Capsule networks. They can also do, capsule networks again, can piece together items in a scene. And it can understand that this is made up of, a mailbox, a tree, a house, and different polygons or polytopes that make up those things and which direction they're all pointed. It has, this model has a lot of moving parts. It's pretty slow to train and use. It's not that bad, but it's nothing about it is efficient. But it does the job better than CNNs. Any questions? Okay. Who has played these? Any of them? Raise your hand if you've played at least one of them. All right. Have any of you played one not on your computer, but on an old system? All right. Tell me about it.
My friend had one at his house. It was Pac-Man. It was like this one on there's an integrated into a coffee table with joysticks on the side. That's
Computer that plays one program.
Yeah,
That's all it does. You?
It was like a pre-packaged joystick that had it built in, and then you could hook it into your TV, which was kind of a pain. But then it just ran.
Nice.
I played Galaga and Pac-Man on actual arcade machines, and my dad's a bit of a nerd, so he got a table that had the two joysticks on the side that had the holding Galaga Pac-Man. I think it may have had some more, but those are some very specific. So, yeah,
All right. So why would these games be super interesting for training AIs?
very limited scope.
And you know exactly what the world is, right? You get a perfect world state. So who here has heard of DeepMind, the company? So DeepMind, purchased by Google a number of years ago, was started by a guy named Demis Hassabis, who's a child chess prodigy, and then decided to get into AI. Well, he's in that too. He was the first guy to develop AI that will solve all of these at superhuman levels. And it was just blow away how well it did. And you would see, learn to do things that humans can't quite do. One thing we all learned when we played this one is that what you really want to do is you want to have a little door somewhere on the left. Maybe you break through either on the left or the right. Then you get the ball up there, and it's just going to bounce on its own, doing your work for you. Well, the model took a while to learn that, but it learned that. And it had to play, millions of games, but it could do that, in 10 minutes, whatever, because it was in a simulated world that happened fast. They were able to do better than human, on all the games except for one that I don't have pictured here called Moctezuma's Revenge. Does anyone know the premise of that game? It's the kind of game where every screen is a stage you have to get through. Maybe you have to find a key somewhere in the room. Pick that key up, then go to a different part of the room, maybe climb a ladder, go down a hallway, whatever, and use that key. Why would that be so hard for a neural network?
And based on what you said, the maps change, and neural networks used to be staying close to the state of the school changes, but what you're saying is they can have an entirely different functional stage with different things. There's this group is instead of being hallways, traps, this, that. So with the changing of how like the dynamic of the games works, it would struggle a lot more to learn that than compared to like Pac-Man or Breaker, where you can just it's almost the same every time. The only difference is there's more walls where there's less variety in that than for monsters.
That's a very good point. And that is true. There's another point as well, though, which Brendan, you're starting to face with what you're working on. He's doing a little, side project thing. When you have a loss function that can tell you an exact answer only after you do a number of steps, it's really hard to do what you should with the previous steps. Like think about Montezuma's Revenge. If you have a room, you have a little guy, he's got a hat on. He enters the room, there's things in the room, I think there's ladders and stuff. Let's say there's a key here. You have to get the key and then maybe go down here or something, right? So if you have the key in your possession already and you exit through the door, then you can tell your neural network, good job, you did great. If you already have the key, I guess you could train it, you could tell it, if you go down this direction towards the door, that's good. But how do you tell your neural network, okay, you need to go this way first, then go this way, and not die anywhere in between? One of the ways we describe a situation like this is you have sparse rewards. So most of the steps he takes, there's no real way to tell it this is right or wrong. I mean, if you're a human, you could program in and try to do that. But what they were trying to do, the whole reason they did this was to see if it could learn automatically from the score in the game. All it's trying to do is maximize the score. And there's a lot of human knowledge that we bring to the game that the computer did not have. As a human, when you see this, you see a thing that looks like a key, hey, that's a key. That is probably going to open doors. And I bet doors are things that need to open.
But you not program that to be realized by a neural network?
You could program that and many other things, but he was trying not to. The whole idea behind the project was, can a neural network learn just from the score? Yeah, that's what they're trying to do. Now, obviously, when you get the key and you go out here, your score just go up. Now, the question is, if you're the neural network, how do you take that reward and apply it backwards in time? What if you actually did a whole lot of really bad stuff, like 15 minutes, just wasted your time, then eventually randomly got the key and went out the door? Do you apply a positive reward to all those many wasted steps you took in the middle? If you do, your neural network's not going to get better at this game. It's a really hard problem.
Those kinds of games don't you usually get score or increased score based off of over time?
Yes, that's right. I don't know if Montezuma's Revenge had that, but if it did, then that would be true, and that could help. It may not be a strong enough signal though.
Well, it would also depend on if the system first goes first instance that it learned, it took a lot of time because then it would assume that it got a high score based on that, and then keep trying to do something. It depends on how it first gets the action.
Does this ever happen to humans? Does anyone have an example?
I mean, for the best and personal example, I wasn't playing a game, but I was doing something with some friends. We were in competition with each other about, I think it was, I don't remember, it was years ago. It was like origami or something, and we were all it was like 10 years ago, and we were all trying to complete origami, and we were all trying to learn it. And someone just came along and said, "You're doing it wrong." And we were all like, "That's impossible, we're following the guy." And they essentially showed us how to do it properly. They finished it in 5 minutes when it was taking us all 30 or 40 minutes. And we had assumed that the guy's correct. So we had just followed the guy immediately and not questioned it at all.
This reminds me of when we talked earlier on about loss functions that lie to us, deceptive gradients. Like, remember we talked about how people, if you're trying to get to the moon, going to the top of the mountain doesn't help, even though you are closer to the moon, right? Well, it's really hard to even come up with a loss function for this. But there's a lot of advancements since then. They've, figured out other ways to apply things backward in steps. Q learning is one of things that have done pretty well here. When I think about humans having this problem, a friend of mine in high school was the pitcher for the baseball team, and they weren't doing very well. But then one day, on the way to a game, he hits a flat tire, and he puts that little skinny thing on his wheel to replace the tire, temporary. And they won. They had their best game ever. So he kept it on the whole season because he was afraid that somehow that was the reason he won. Now, it's a silly example, but we all know people who are a little superstitious about sports. There's certain, clothes they have to wear, things they have to do, and they feel like it matters. That's kind of the same thing as what's going on here. There's a reward, and you don't know exactly what to apply it to. Okay. Let's get into generation. So in the same way that a neural network can recognize something, you can also play it backward the other way and generate something. So let's make a face generator. All that really means is we have some big network, which is probably that convolutional neural network we looked at before. The really long thing with many filters and colors and all of that. So on the input, we just give it some random noise. And the output is the number of pixels in the kind of images we want to generate. Separately, we're going to gather from the internet millions of real faces in that same aspect ratio, the same number of pixels. So now we have two sources of faces. And at first, one of them are going to be the real faces and they're going to look real. And the other source, they're just going to look like garbage at first, just noise. And you take these two things and we know which one's real, which one's not. Now, we send them through the discriminator. The discriminator is another network of approximately the same complexity. And it just has two outputs. Is it fake or is it real? And if it says for the fake one that it's fake, good. If it says the fake one is real or the real one is fake, then we have a loss and we propagate that through here. Now, this one, its goal in life is to trick the discriminator. So it generates something. If this image gets correctly classified, then this one gets lost. And this one gets adjusted so that it gets better at fooling this. So you have this training, then this training, then this training, then this training, and you keep doing that, and eventually you get something that can generate very realistic faces. And they're just getting better at this every day. But some of these are, I have some here. These are from over a year ago. These are generated. These people do not exist. They were never born. That guy in the top right never wore glasses because he doesn't exist. But they look so real. This is over a year ago. They've gotten better at it since then. Another thing they can do, even over a year ago, is they can take an image that they generate, and then they can have sliders. They can slide, okay, male to female, black hair to red hair, young to old, change the race. They can change every feature as an individual feature right in front of you, and you'll see an image of a young boy, and they'll change it to an old woman slowly, and it's like, yeah, every little bit of that slider, it makes sense, It's amazing what we can do. But these people did not exist. Now, these are good examples. If it were to make mistakes, though, what kind of mistakes do you think it would make?
Assume one black hair. So probably some like weird blurriness.
So the hair mistakes.
Getting eyes and smashing the face as well.
Mhm.
I want to see something we could use.
Well, I collected some screw ups. The guy in the top left, is he wearing glasses? I see edges of glasses on going to the ears and stuff, but there's no actual glasses in front of his eyes. Okay, it's a nice looking woman, but what is this? It's a weird little humanish kind of area that is not recognizable to be anything. Another nice looking person, but to the top corner, what is that?
Dude, that's their killer.
It's like, it's person-like, but there's issues. And then, of course, this poor woman and her fingers are fused into her face. What's wrong here? I don't know if you can see from where you are.
So like the background's tilted.
Nope.
The reflection of the glasses.
Yes. Yeah, the reflection glasses. I mean, even if one of them's right, they should both be similar. They didn't get that right. And again, here we have a person with an eye that's just who knows what's going on there. So these are the kind of mistakes that neural net will still make. And one of the new things that come out of Google is called Imagen, IMAGEN, and it can do video. And it has weird aspects to it. So let's say you ask it to imagine a teddy bear walking through Times Square. This is one of the kind of things to do, or skateboarding through Times Square. Now, every time you were to ask it to do an image, a still image, it will do it differently every time. Video means there has to be some temporal continuity, where the pixel before the image before leads to the next image in a way that makes physics sense for movements. And it's doing great in terms of, we're getting there, but it still looks weird and it makes a lot of little mistakes. I saw a video of a dog running on the beach, and there were times when the face changed into a giant tongue, and it was just, and then the face came back, and it was the computer doesn't understand things like permanence of physical objects and what those objects are. Are they soft? Are they hard? Are they malleable? Are they liquid? It doesn't really know. It's just working in the space of pixels, literal pixels in 2 dimensions. Okay. Okay, translation is another very hard problem to get right. It's my personal favorite of all the AI problems that we have to solve. Is my personal favorite. This just shows you one of the weird things you have to think about. There are three main approaches to capturing the CO2 generated from a primary fossil fuel. And in German, es gibt drei Hauptansätze zur Abtrennung des bei der Verbrennung. Now, this is a word that's not in the English. Verbrennung eines fossilen Energieträgers entstehenden CO2. So, this is burning. The word burning is not in the above, but it's still the correct translation because it's implied. One of the hardest problems to understanding language is how much is implied. And one of the ways you can see how hard of a problem this is read old books. If you read old books, you may come across words you don't know or just things that you don't understand. Like one thing, I was reading a book from the 1800s one day, early 1800s, and it mentioned second sleep. Does anyone know what second sleep is? Apparently, in the days before internet and Netflix and electric lights at home, people would go to bed when the sun went down. But no one in the winter wants to sleep, 12 hours, 13 hours, so they would get up for a midnight snack, maybe light a candle, eat, and then go back to bed for their second sleep. This was something that the book I was reading didn't have to explain because it was assumed that I would know this because everybody knew that. But then as our lives changed, we stopped using that term. So burning is implied. It's not in the text, it's implied because we're humans and we know a human wrote that and we know what they meant. There's so much data in text that's not in the text. It's in the implied models that unpack it in our brain. And that's one of the hardest problems in AI to get right. Okay. You're doing neural networks for your homework right now. If you look at this, there's a link here at the bottom that explains more about these. This is some guy who took a number of different data sets, kinds of data, you can see what the data sets are, and he trained a random forest, a neural network, and an ensemble model, which is both of them together, on every one of these. Loss is on the left, so lower is better. And what you see here is that neural networks never win. Very interesting, huh? Neural networks have such a great reputation. Why does a random forest beat the neural network basically every time? I mean, it kind of ties in the top right, but why would this be happening? And if it's true, why would neural networks still be so popular? I guess a neural network is like more than one thing. It's more general, yes. If you don't know how to deal with a situation, a neural network can do it. Now, maybe you can figure out how to set up a random forest to solve it too. Maybe you can't. Neural networks are more general, they're more applicable, they're kind of more fun, and you can just throw the kitchen sink at them, throw as many kinds of variables you want in there, and they just work. But they oftentimes won't give you the best accuracy. Now, there are situations where I believe they do better over time, but it takes a lot of training. Millions of examples. Millions. Okay. Who knows what's going on here? This is adversarial AI. I mentioned it a little bit ago. Let's look at this example. So we have an image of a panda, and we have a trained neural network that's trained to recognize animals, okay? If you ever want to play with one online, YOLO is a good one. Teacher is another good one. And there's models you can download the weights yourselves, play with them, and you can retrain them for whatever classes and things you want. Now, the panda to us obviously looks like a panda. But what's weird is if you do it just right, you can take this image, add these values just a little bit. You put a very tiny gradient on, a very tiny learning rate on that. Just add this to this image. But like for this picture right here, where it's making it more purple, you're only adding like 0.001 of that. So you make this pixel a little more purple, this one a little bit more blue, this one more blue, maybe this one a little more red, magenta, and this one white. And you end up with an image that looks like this. I mean, the pixels may have changed just one or two in either direction, higher or lower, in the R, G, or B. As a human, you can't tell the difference. The image looks the same to a human, but it totally messes up the AI. Now the AI sees the thing and says, it's a given. I'm sure it is. This was discovered in 2014. Ever since then, scientists have been hard at work trying to make robust neural networks that can't be beaten by this method. And there were 3 lines of research that were all very promising. They all said, we did it. And then a guy named Nicholas Carlini came along and showed that no, they're all still just as breakable. Sorry. There's no end in sight. There's no solution, basically, is what he's saying. So every neural network seems to have this brittleness. And the way we can explain it comes from looking at the right class. So if panda is the correct class, then if you look at some variables, some input features, maybe x0 and x1, the y is going to be the output value for panda. So x0 and x1, let's say their initial values are right here, let's say. So this line, this height, represents the probability that it's a panda given this x0 and this x1. Now, what you want is a neural network that will be like, okay, if this x0 was a little bit lower, like here instead, and this x1 was a little bit lower, then the line would still be high. This value would still be high. Or if it's over here, it's still high, you hope. And over here, it's still high. And over here, it's still high. That's what you'd hope, that little changes to these, it would be stable. Now, let's say x0 and x1 are actually one color pixel values. So if we have, 1,000 pixels, that's 3,000 values. So we have x0 all the way to x3000, basically. Now, if these are 2 variables for which this is stable, then you'll find that anywhere in this area, it's going to be high. You're going to get a surface, a high surface, and that's nice, it's wonderful. But out of 3,000, do you think that's always true? It turns out of those 3,000, or if it's a high definition image, could be 1,000,000 pixels, 1,000,000 inputs. So somewhere in there are going to be 1, 2, or 3 features that this is not true for. Instead of having a nice stable surface, you will have a cliff. So maybe it's stable here, but then there's this drop off cliff. And the original starting point of x0 and x1, you just have to go a tiny little bit in one direction. And now the probability that it's a panda, according to the neural network, goes down to almost 0. And it turns out these areas after a cliff, they correspond to images that are unlike any seen in nature. In nature, there are certain, not just that kind of nature, but any physical image that you take on your camera, there are certain distributions of pixel values that are reasonable and seen in the world. And then there's ones that are not, represented by, doing points like this. And the neural network generated this to push it off that cliff. And remember, out of 3,000 dimensions, it's just got to find the right direction, the shortest direction to that cliff. And then it pushes it toward that cliff. And remember, we've got 3,000 dimensions to play with. So you add a little bit to this dimension, and then, x 547, you add a little bit of blue. Get the idea? It's kind of magical and fun, but also scary. Have you seen memes online about what people have done to trick neural networks? What have you guys seen?
I saw an image that somebody found that they had pulled out from the Tesla that would cause it to track or whatever it was.
Yeah, that's scary. That's where it gets really scary. And since we know, because of Nicholas Carlini, that neural networks will always have this problem, Teslas will always have this problem. Now, humans have many more problems. So realistically, Teslas and other self-driving cars, they just have to be maybe 1,000 times safer than a human, and then we'll allow them to drive. But still, they will have these exploits. But it's not something new. Humans have the exploits too. You can, cause a human driver to make a mistake by shining a super bright light in their face. There's a lot of things you can do, mess with humans and neural networks as well. We all have our weaknesses. Okay, who knows what this is? It has a certain name. It's somebody's model, and it's actually on the screen. Yes, the von Neumann model. So von Neumann was one of the scientists in the, Los Alamos Manhattan Project, one of the smartest people in our country at the time, and he came up with this model for designing a computer. You have some input, which was not originally your keyboard or the internet. Anyone know what the input model was? The input device? Punch cards, yes. Where do we get punch cards from before computers? They were borrowed from other technology. Nope. Something going back to the 1700s. Nope.
Music boxes that have the bronze that blue when they pass over space.
No, but it's a very good idea. And player pianos actually had something similar. But before that, no, but that's a great idea. That was Charles Babbage. And that reminds me, remember we looked earlier, the woman who invented assembly language? Well, a woman was the first computer programmer ever, Ada Lovelace. She invented computer programming for Charles Babbage's machine, which he never finished. They had to finish after he died. No, punch cards come from the making of fabric. So if you have a loom, some giant machine that has a bunch of different, cross threads, and you're trying to figure out which color next to lay out by weaving through with a shuttle. You have a little shuttle, this piece of wood or something that drags along another color thread. Let's say you have multiple color spools that you can draw from. Punch cards were designed to control a loom and decide which shuttle would go next. If this hadn't happened first, we may not have gotten computers when we got them. We may have had to wait around another 10 years and invent something, who knows? Anyway, so they borrowed that for the input device. Now our input devices are different, but it's still the same structure. We have input. Then you have in here a CPU and memory. This typically, we think about this as your hard disk. You could also think about it as RAM. But whenever you have a CPU and it's got control and arithmetic inside, it goes out and asks something from the memory. And it gets that thing back, it does something with it. Maybe it stores something back to memory and it outputs. It's centralized, meaning all computations are done in that CPU, and it's clock driven. You take a computation now, take it now, take it now, take it now, and everything's structured. Are there alternatives to this that you guys have heard of? Well, one alternative, let's say first, let's look at this. This is why we might want alternatives. This is a logarithmic scale. The brain does more with such less power. So many more flops per watt. It's amazing what we can do. Better than the best GPUs. Now, GPUs have tons of processors, but every one of those processors is like the von Neumann model, von Neumann architecture. Okay, here is an alternative. Distributed and event-driven. Another word for this is neuromorphic. And what you'll have is that instead of having a CPU over here and memory somewhere else, and you go there to get some memory and you bring it back and do stuff with it, every little computational unit has some local memory. Not much, just a little bit. It doesn't know much, just knows what it knows locally. But it can compute and change its memory state and pass on the computation to other units nearby. And maybe you'll get answers out one edge. And it can be event driven, it doesn't have to be clock driven. In fact, theoretically, you could have every one of these operating individually, separately, not on the clock, maybe not even in the same rate as each other. Okay, neural networks, you've seen that? This is a simplified model of your cortex. So neural networks, first invented in 1958, they were trying to take a neuron, like what you see on the left, and duplicate it in your computer. They were inspired by the brain. So let's take that information a little further and look back at the brain and see how we're doing. If you look at the neocortex, this is the part of your brain that's on the outside. If you were to take it out of your head and put it on the table, you can actually flatten it out. If you undid the grooves and the sulci and the gyri, you undid those and flattened it out, it'd be about maybe this big and about 1 inch thick. And it turns out it's the same kind of cells and the same structure everywhere. The part of your brain that controls your fingers is same as the part of the brain that's doing vision, that's doing sensing my left knee, to thinking about what I'm going to do tomorrow. They're approximately cortical columns. You could, in some ways, subdivide this sheet, 1 inch thick, into maybe 100,000 of these cortical columns. The division between the columns is not so clear. very hard to see in humans, but it's approximately there. So this is a model, thinking about it, nothing's perfect, it's a model. And when you look into one of these columns, you'll see approximately 6 layers of neurons. Let's see if there's another one. Yeah, here. So approximately 6 layers of neurons. This is on the inside, that's the outside of your brain, the outside layer. So you have information mostly flowing up from the brainstem and your emotions and your nervous system, but also coming in from the top. So it doesn't flow one way, it flows both ways. That's one difference between your brain and the way we've done neural networks so far. Another difference, which is very strange, if you look at an artificial neural network, which is what we've been doing, let's say you have a bunch of neurons here and a bunch of neurons in the next layer. Every neuron in this layer is connected to every neuron in the other layer, but never to a neuron in its own layer, never. It's the opposite, almost the opposite in the human brain. There's a lot of connections within each layer and very few connections between layers. So they're connected up very different. And the third big difference is there's a guy named Blake Richards who did very interesting neuroscience and deep learning research. I think that's his name. He's got some great talks online, but he talks about how it is impossible for the brain to do back propagation. It doesn't do back propagation. It does something else. No one's quite sure yet what. And that's probably a good place to stop. Any questions?